All right, so we're starting off with descriptive statistics. The name of the unit is describing and displaying data, but it essentially falls back to descriptive statistics, I guess, descriptive describing, so there you go. But also displays. And what we want to have is the flexibility to use technology in the displaying part, right? Because creating graphs by hand, while a fun use of our time, actually uses time, right? Whereas the calculators, Excel, Google Sheets, things like that, they do it much more swiftly, right? So yeah, we're going to learn about those concepts, but we have to start with the basics. Measures of center. And this happens every time. Hold on. I have to disconnect. Open this, turn that on, go to Apple Pencil, and close that, and come back and try it. Open this, change something, plug it back in. That'll connect again eventually. I've been having trouble with the Apple Pencil because it keeps just randomly disconnecting on me, and I have yet to figure out why that's the case. And my hopes of having a really great video that I don't have to edit later just went out the window. So let me try this one. I turn that off, let it think for a second, turn it back on, and go back in. Try it again. Try it again, and turn off Wi-Fi. Try it again. This is the definition of just pushing buttons until something works. So far, it's been a successful strategy, but I think my luck might have run out. So then what I'll do is what I did last night. You're getting a finger stylus today. Alright, so yeah, like Apple is kind of taking over the world, but they do whatever they can to make people actively hate them. And here I am. You know, it's like new phone doesn't fit the old charger. You know, like, what are we doing here? You know, you have this Apple Pencil that connects nicely with a lightning port, but nah, we're going USB-C now. Thanks for nothing. So it is what it is. We're gonna start off with the mean. We use the symbol X bar, really anything bar. I'll try to give you a sense of where I am on the page, and so you know what to do with it. Average of all values in the set is denoted by X bar, X representing a random variable, right? I should say just a variable, because we're not at the point where we're incorporating randomness to it. But it's equal to a really interesting looking formula. The sum from I equals 1 to n of x sub I all over n. I have to write it like huge because I'm using my finger, but I'm going to resize it as I go. So don't think that you, on your paper, you know, because some people try to map it out the same way the paper does, like, don't write stuff like super huge like that. I just have to do that because you won't know what the heck I'm trying to write. Right? Now that's a formula right there. All right. What that means is actually the definition of mean. It's add up that little summation symbol, capital sigma, Greek letter capital sigma. It means sum. The x value is the individual data value, right? Oh, sorry, this is a typo that's been there for like 20 years. That little x should be an x, oh boy. Should be an x with a subscript of I, right? So put a little subscript there, because this x sub I corresponds with that x sub I. And I know it sounds funny. If you're not a math person, you're like, x sub I, what the heck are you saying? The sub means subscript, so x with a subscript of I. But that's a lot to say, so we just say x sub I. All right? We could use that formula, but we could also use, you saw it on NumWorks earlier, we could use a function in the calculator to do it. Right? So it's just a question of strategy. And also level of interest in theoretical math. I mean, you could look at this and say, well, that's fascinating, I'd like to explore it more. Or you could say, can we not do that ever again? You can go either way with it. Right? So this list of data here in that first example, I'm going to bring it in again. That's my x sub I list. Put a colon there. Right? It's the list of all the x values. Right? The denominator, the subscript corresponds with the position within the list. All right? So this is my first value, my second, third, fourth, fifth, sixth. Yeah, 6 values overall. You know what, I'm just going to move that up because that went off the rails pretty quickly. I'll put it underneath it. All right, first, second, third, fourth, fifth, and 6 values. All right, so for example, if I say x sub 2, I'm saying it's the second value in the x sub I list, right? Which would be 17.5. Right. Now what they want us to do is find the sum of all the values in that list. It's just pulling it from the formula is kind of tricky. If you're not familiar with the notation, you know, if you've never seen notation like this before, this is kind of jarring. But what this is saying is start from 1, go to the last value, plug those numbers into the x sub I for the I, and then go from there and find the sum. So what this actually translates to is, I'll show you the expansion. X bar is equal to, we would take the sum of x sub 1, x sub 2, x sub 3, 4, 5, and 6. Right. And we stop at 6 because that's the last value. Right. And then we take that, whatever that result is, and divide it by n, which is the number of values in the set. N equals number of values. All right. And in this case, it's 6. So I would add whatever the value is for x sub 1 to whatever the value is for x sub 2. Instead of scrolling all over the place, I'm just going to look at this. So I'm going to take my 15.1. I'm going to add to it 17.5, 18.3, 14.1, 3.2, and 6.0, but just 6. I'm just going to smidge it over so I can get it in. And divide that result by 6. Now, if I were in your position, I'd be saying, wait a minute, I've learned about the mean. I've been doing that since I was in 4th grade. I've never had to do it like this, and you never will. This is just to give you an idea of where the process comes from. You know, so there's a formula that's used to determine the mean. It expands to this line here, and then when you sub in your data, you get what you always knew the mean to be. Right? You add all the numbers in the set, and then you divide by the number of values in the set. Right? But this gets at why you do that. Right? And I know, if I would say, I'm always a little nervous about saying the wrong thing when it comes to this, because, like I'm in a class with an enrollment of 30 students. Some of you love math, some of you hate math, everybody else kind of falls somewhere in the middle, right? So, and it could be a matter of like 2 of you love math, 20 of you hate math, and everybody else is in the middle, the other 8 people. But I don't know what the actual breakdown is, so I always want to make sure that I'm giving a little bit of something to everyone. So the people who actually really do enjoy this sort of stuff, I don't want to be like, well, we're going to skip this because this is like hard and stuff. I want to make sure we touch on the important things to get questions right, and also make sure that people who like to understand the inner workings get a little something out of it. All right. That being said, I have a calculator. So this is the theory behind it, but ultimately on a test, you want to get stuff right. So you could do it like this, but then you could also whip out a calculator and go that route, right? So I can add these numbers, so that's what I'll do. With NumWorks, a little thing to be mindful of, if you need to have like an expanded fraction, lots of sums and differences in either the numerator or the denominator, you want to hit the division sign first. Even though it's going to say answer up top, we're just going to clear that out, because we want the calculator to know that we're trying to put in a fraction, right? Because what's going to happen if I typed 15.1 plus 17.5 and so on all the way to 6, and then I did divide by 6, it's only going to divide that last number by 6, all right? So I'm trying to avoid that being an issue. So I'll put the 6 on the bottom, so I'm really essentially working bottom to top. Hit the backspace, get rid of all that stuff on the top, and then pop in my 15.1, 17.5. No like fancy calculator stuff going on here, it's just typing it in. Alright, so when you get that in there, you hit either OK. You see OK right next to the home button, or down at the bottom you can hit the EXE, the execute. Either way, both of them do the same thing. Right. So I'll hit OK. And you get this number. We typically want to round our answers. I mean, you don't want to write an entire decimal, although this one could be converted into a fraction. You can do that. If it's simple enough, I mean, if it's like 12.75, I mean, there's really nothing to do there. You just make it a 12 3/4, but it's really the repeated decimals that we want to either round or convert to fraction. This is a data analysis course. Data is typically not represented in nice, neat fractional form with beautiful simplified radicals. It's usually some kind of disgusting decimal that we have to clean up, all right? So that's what we're going to do here. And our decimal, or I'm sorry, our rule of thumb, 3, 6, 7, when it comes to rounding, is that we go 3 significant digits, all right? 3 significant digits, very important. There's been data analysis related to that, and what ends up being the case is if you round to the nearest hundredth, you end up sacrificing a significant amount of accuracy. If you round to the nearest, so we're at the thousandth here, if you round to the nearest 10,000th, you do not gain much more accuracy than rounding it to the thousandth. So rounding it to the three decimal places is really the way to go. But we run into instances where sometimes the first 3 decimals after the decimal point, the first 3 values is equal to 0, and in which case you'd have no way to compare your data. Like, let's say you have one value that's 1.0015 and another that's 1.0025. If you round to the nearest hundredth, they both give you the same value, you wouldn't be able to establish a size relationship. And it would be minuscule anyway, but it still might be meaningful, right? So I'm just going to detail it up here. When we talk about rounding, we want to go to 3 significant digits. Right, for those of you who excel in the sciences, you might have heard the term three significant figures, or any kind of significant figure, sig figs. That's not this, right? So I know that when I first heard this term as a student, significant digits, I had like flashbacks, not in a good way, to chemistry, and then belatedly I realized no, that's not the same thing. This is much less complicated. I find that the best way to explain this is through example. So I just gave you one there, but I'll make up maybe two or three. So I'll say, this is my way of saying example. I'm gonna bring it in real, like a lot to write it, and then I'll pull it back out, sorry. So let's say you have 1.001247. And another example of 1.001072. The two examples should be all right, because I just did the third type of one in the problem that we did. All right, so three significant digits tells us you start off at a decimal point, and you look to the first value to the right of the decimal point. If that's a zero, ignore it. Move on to the next decimal, the next value. If it's a zero, ignore it. Move on to the next one. If it's a zero, ignore it. Move on to the next one. If it's a zero, ignore it, but in this case it's not. So this would be the first of the three significant digits, right? Once the zeros stop, you have a string of zeros following a decimal. Once the zeros stop, then you start your count, right? So 1, 2, 3 places. Then we would cut it off right here and use appropriate rounding rules to round it, right? So the whole 5 or above, give it a shove, and if it's below, let it go, something like that. So this would be 1.000125. All right. The next one, oh, and just a word on the previous example that we did. Sometimes immediately after a decimal point, you have a non-zero value, like we did here. In which case, the process of rounding to three significant digits is the same as just going 3 decimal places. All right. I tend not to overly deduct points on tests when people mess up rounding, but it'll cost you, I'll say it'll cost you at most a point on a free response question, like if you round incorrectly. And those questions are worth 10 points, so it's not that crazy. The area that you gotta kind of worry is with multiple choice questions. Not because I'm not a jerk, so I'm not gonna put 2 answers that are really, really close to each other, with one having a rounding mistake and the other not. But what could happen is that you could make a rounding mistake very early on in the solution to a problem, and then it carries its way through, and it spirals out, and you end up with an answer that's way different than one of the choices that are there. Right? And you end up selecting the one that's closest to what you think the answer is, and it's wrong not because you rounded in the last step incorrectly, you rounded in the first step incorrectly, and it compounded along the way. Right? So we want to be careful about stuff like that. I'll talk more about rounding in the future. I have different ways of making it as important to you as it is to me. For the next example, see I have the 2 zeros. I'm going to ignore those. I'm going to start my count at the 1 and still go 3 places from there. Right? Even though the second value after I start my count is a 0, that's still part of the 3 significant digits. Right? So I'm going to cut it off right here. That's been a misconception in the past. People with the idea that, okay, if it's a 0 at all, we ignore it. No, once you start your count, you continue your count. So it's only for a string of zeros immediately following a decimal point that you ignore them. But once you get a non-zero value, you start your count 1, 2, 3, round appropriately. This one would be 1.00107. All right, because the 2 is below, so we let it go. All right. Now the good thing about the NumWorks, and actually I want to be fair to TI, it does a lot of this stuff okay also. but the copy paste aspect of NumWorks is kind of like a next level thing. I mean, honestly, it should be standard in like every device ever, but for whatever reason, TI hasn't really got a handle on that. Yeah, so if let's say I'm doing like a 5-step problem, and so after step 1 I have a disgusting decimal, I don't want to round that, I want to use the actual decimal, I can copy it and bring it into the next app, paste it in there, and then, you know, off to the races. So that's a good thing. So yeah, let me show you for this example the mean. Another way to do it. It's in the statistics app. Right. I'll make a little note of it. Where do I want to do? I'll just do it at the top here. Statistics app. Right. So what you do is you go home, you hit the home button, and then you go to the one that says statistics. All right, so you hit the home button, you go to the one that says statistics. All right, then you hit OK on that, or execute, it's up to you. Again, they both do the same thing. Kind of begs the question why they have 2 buttons. I have not come across any functionality in this calculator that distinguishes execute from OK. Like they're all, as far as I know, used to accomplish the same thing. Maybe in a future update. Oh, that's the other thing I wanted to mention. The NumWorks calculators, and by the way, I'm singing the praises of these things. I don't get any money from them. They don't give me free stuff. Like I just like the calculator, so that's why I talk about it. And I think it's good. So, and it's like I mean, the ship may have sailed for a lot of you, but it's College Board approved. So if you have to take a College Board exam for any reason, is GRE College Board? Yeah, I mean, it's so pervasive that you never know, but it is College Board approved. You know, like when I say college, like AP exams, SATs, ACTs, things like that. Right. So, but you never know, and you don't have to buy anything. I mean, if you go sit for an exam, you'll have to probably buy one, but you know, that's a different story. Statistics app, hit OK. Now, I just landed in a place that's probably way different from where you would land. So if you're using the app on your phone, on a computer, when you hit statistics, you came somewhere else. All right. That's because this calculator remembers the last place you were and brings you back to that place. All right. So to make mine as similar to yours as possible, I'm just going to do, actually, I don't even know if it'll do it on the app. Yeah, in the app, it doesn't even, with this app, it doesn't let me reset anything, I don't think. So it was worth a shot. But what I'm going to do, because this is a display of, we call it summary statistics, right? Data has already been analyzed, but it's not the data that I want to analyze. I want to analyze this data. So that's a little dark. That's the data I want to analyze. I want to find the mean of that, the X bar. Now, if you go down this list, you can see there's one that says X bar, the sample mean, but it's related to stuff that's completely incongruous with what we're working on. So I'm going to go back in. Sorry, I'll bring it back to the place I was at. If you're in a menu you don't want to be in, you hit the curly back arrow. It's very subtle, but it just brought us to that top set of tabs. I'll do it again. So I was around here somewhere. I hit that curly back. It brings me up to stats. Now I can go back and forth to the different options in that top row. I can look at a graph. Again, it's not related to what we want to analyze, so I'm not going to do that yet. I can go to data and hit OK, and now I'm in a data editor. All right, this is for those of you who are familiar, it's StatCalc 1 on the TI calculator. Right, it's also basically serving the same purpose as a column in an Excel spreadsheet. Right, but it only accepts up to 100 values. Right, now I have all this data in here. Useful skill. I want to be able to get rid of data, especially if it's lengthy like this. I got like 30 values. I don't want to have to backspace on every one of them, up, backspace, up. That takes a while. What I do is I backspace on the column heading, says value V1. I'm gonna hit the backspace on that. Then I'm gonna confirm, and it's gonna wipe out all the data. I don't really need to do it for the other data sets, but I'm gonna do it anyway. So I'm gonna hit backspace and confirm. Up to the column heading, backspace, confirm. Alright, so what I wanna do is put in this information. Now it's organized horizontally here, that's fine. I wanna put it in as a column though, I don't wanna put it in horizontally. First off, I only have so many columns to play with. Like, I think there's a maximum of 6 of them. That'll work in this case, but if I have more than like 6 values, I don't have enough columns. So we do it vertically. I type in the 15.1, hit OK, to lock it in. You'll see in the frequency column a 1 appears, right? All that's telling me is something I already knew. I typed in the number 15.1 once. That's all I got from that, right? So you can ignore it is what I'm saying. So 17.5, lock it in by hitting OK. 18.3, lock it in by hitting OK. 14.1, same deal. 3.2, and 6. All right, so we have our data in. We can do a couple things now. One, we could find the mean, which is ultimately what this question is asking us, but I could also make a graph. I could find other measures of center like the median or the mode. I could find interquartile ranges, standard deviations, a lot of different possibilities. Basically anything that can be done with data will be done using the steps I'm about to show you. All right, so I'm gonna go up. Now that I have my data in, I can hit the up arrow until I get to that top row. Again, that top row is how you toggle back and forth between the different features. I can go left and right. Yeah, question?
How do you imagine you press stats on the calculator, but what if it doesn't work?
If it does, so, like, you're talking about this statistics menu? So, you hit OK on that, it didn't work for you? Huh. Here, let me have a look. Yeah. Oh, gotcha. Yeah, I should have mentioned that, folks. I didn't. I don't really like this aspect of it, but even though it's an app on a touch screen, you still have to treat it, because it's an emulator, you still have to treat it like an actual handheld calculator. All right, so when you're in this home screen, you really, really want to be able to say, all right, stats, we're in, regression, we're in, but you have to use the arrows up, down, left, right, toggle back and forth, yeah. Because it really is emulating how a graphing calculator would operate. So, for better or for worse. So anyway, we go right up to that column heading. I'm going to go over to stats. I'm going to select OK. Right? Now I mentioned before that there's an X bar in this list. So I'm going to go down and find it. X bar, sample mean, right? The question here just said find the mean of the data set. It's implied that the data set is a sample, but you know, I probably could be a little bit more specific about that. So I would say find the sample mean. Ah, boy, oh boy. So find the sample mean of the data set, all right? And if you look over, you have your sample mean, the X bar. It's hard to see on the big screen, but that does say 12.366 repeated to a 7. right? So we get the same answer in a fraction of the time. Right, but again, the point behind doing all this stuff wasn't to show you a way that you would do it on a test, a quiz, or something like that. It was to show you the inner workings of the process, right? I'm actually going to do the same thing with the median and the mode. The mode's a little simpler, but the median. One technique. There's a bunch of different techniques for finding medians by hand. I just kind of settled on this one because it was the simplest one to explain. But what you're going to do is you're going to sort the data in increasing order. Ascending or increasing order means the same thing. We count down to the middle. If there's only one value in the middle, that's the median. If there are two values, then we find the average of those two values. All right? And again, average, another word for mean. I'm just going to write that again. Right, so the average is another word for the mean. So first step would be to put it all in increasing order. So I'll start with the smallest value that I see, which appears to be a 1. Then the next smallest, which is a 2. You can cross them off as you go if you want. 3, 4, 6, 8, 9. Then the 14 and 20. The 9, 14, and 24 are actually all in the correct order to begin with, so that's good. So we had to basically unjumble it. Right. So then we count to the middle. Alright, so I'm going to count one step in, 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 last step, last step. Now, so I get the median equal to 6. If my numbers are in increasing order and I have an equal number of values to the left of what I'm calling the median and an equal number of values to the right, then I'm good. I have 4 values that are less than 6, 4 values that are bigger. 6 must be the one in the middle. All right. Oddly enough, the weird notation for the mean doesn't really carry over to the median. The notation to represent a median is just MED. All right, so MED is equal to 6. All right, so the next one would be, it's essentially the same idea. So I'm going to start off with the smallest, which is 0. Next smallest, 1. I have a couple of 2s. 3, 4, 5, and 6. All right. So 0, 1, 2, 2, 3, 4, 5, 6. I'm going to do the same thing. I'm going to count in the middle, or into the middle, but something slightly different happens here. All right, so here's my outermost value. Slide inward. 1, 1, 2, 2. 3 steps in from each direction. But if I go any further, there's no value there. All right? But we can assume a value. I'm going to look for a value that's directly in between the 2 and the 3. The way to figure that out, MED equals, is to take the average of the 2 and the 3. Now, if we know conceptually that it's directly in between 2 numbers, and those 2 numbers are consecutive, then it's going to be a half unit. Like what's a number, what's the value that's in between 2 and 3? You say 2.5, okay? And that's exactly what's happening here. So you could write it as 5 over 2 if you want. You could write it as 2.5, or you could use the mixed number 2.5. I just I don't think it's based off of the way statistics works and my experience with it, I don't think it's the best idea to go with mixed numbers. Fair, you know, like every now and then is fine, but you'll find, especially when we get to the probability unit, that kind of thing sort of works against you, right? So stay with the decimal or a fraction, a single fraction, even if it's improper, just leave it like that. And you'll always have a clue as to what kind of answer you should expect, because on a test, you know, if it's a multiple choice question and the answer is going to be a decimal, those multiple choices are all going to be decimals, right? So you'll know, all right, I shouldn't really be looking for a fraction here anyway, right? For the mode is the most frequent value or values in the set, right? So there could be none, there could be more than one. So I want to find the mode of these 4 data sets. I did 4 examples here because each one brings a little something different to the table. To the best of my knowledge, there is no abbreviation for mode. So mode equals and then you just look for the most frequent value in the set, bearing in mind that there could be more than one or none. All right, so in this set, it appears that 7 occurs more than every other value, specifically twice. Oh, sorry, yeah, that's 7. All right. There are some instances where you might be interested in how often the most common value happens. That's not something we are really going to bother with, but they call it a modal frequency. So that's where I went there. All right, but the mode itself is 7. That's the one that occurs most often. For B, every value occurs equally as often as every other value. So there's no single value, or maybe 1 or 2 values, that occurs more frequently than the rest. So we would say none here. For C, the 1s occur twice, the 3s occur twice. Let me get a lighter one here. Go orange. I don't even know if that's on there. It looks orange on mine. So we have 2 modes, right? Because they both occur more frequently than the remaining values in the set, but neither of them occurs more frequently than the other. So we would just say it's a tie, the 1 and the 3. And then the last example, yeah, there's some repeated values, but it's not whether a value repeats that makes it a mode. It's the one that will repeat most frequently that is the mode, and that's the number 3. The 1s are repeated, the 2s are repeated, but the 3s are most repeated. Right? The mode is something that, yes, you can get it from a graphing calculator, but for small samples of data, it's usually easy to just pick it up just by looking, right? Because you don't want to find yourself in a situation where you typed a whole array of data in and then found out, you know what, I could have done that by hand and it would have only taken 5 seconds. You know, just the act of physically typing it in could take longer than you're comfortable with. But let me go back to the median and show you on the calculator, right? It's really the same function, but I'll use the calculator to verify my answer to A, right? So again, when you're popping stuff into the calculator, you want to be in the data menu, all right? So you see my cursor's down here in this neighborhood. If I want to get to the top, that row at the top where it says data, graph, and stats, I hit the curly back once, left arrow over to data. I have all this data from before. You have a choice here. You can just overwrite the data values if you want, that's fine. Or you can clear it out the way I showed you before. All right, that would be up, clear, and then hit confirm. Right, so right arrow, confirm, and it wipes it out. Right, if the amount of data that you're typing in is more than what's already there, then you can just overwrite it. Save yourself a step. All right, but again, I'm gonna tackle this one in the calculator. So the median example A, so 6, 8, 4, 3, 1, 6, 8, 4, 3, 1, 2, 9, 14, 24. Most of the stuff that I mean, I know learning a new form of technology can be tricky, but most of the stuff that we do, it's going to be reliant on the calculator. The calculator is going to do it for us correctly. The only thing the calculator needs from us is to type the data in correctly. It's going to do everything else for us. It needs to rely on us to type it all in correctly. All right. So I'm going over to stats. I want the median. Fortunately, there's one right there that says median. Look at that. All right, and that's what we came up with for that question. Now, if I wanted to find something like the sample mean, I can get that too. If I go all the way down to the bottom, it does not say mode, but it only doesn't say mode because there is no mode. All right, if there was a mode in this data set, it would have identified it here. I'll show you real quick. I'm just gonna adjust the data, throw in a couple more threes. All right. So you go over to stats, roll on down to the bottom. It says the mode is 3, and that mode of 3 occurred 3 times. If I have, let's say, what did I say? 3 times? I meant 4 times.
4, okay.
Yeah. So let's say 30, 30, 30, 30. All right. So up and over, all the way down to the bottom of the line. It'll identify each unique mode, the 3 and the 30, and it'll tell us the frequency. Right? The frequency is the same for both of them, otherwise it wouldn't be the mode. Frequency is just how frequent something occurs. Right? The frequency of something is just that, the root of frequent. Right? It'll also give us things like the range in the mid. It won't give us the mid range, but it'll give us the range. Right? If you go up towards the top, you see an option here, range, capital R. For the data set that I already had in there, it was 29, but range is not difficult to compute by hand. Most people are fine with that. The only exception is if you have like 100 data points and you're having a hard time identifying what the smallest and what the largest values are, then you want technology to do it for you. But here in this example at the bottom, it really is just a matter when I want to find the range of taking the max minus the min. So that's going to be 17 minus 1, which is 16, right? 17 minus 1, which is 16. And that's the range. It's the displacement from the smallest value to the biggest one. How many steps do I have to take to get from a 1 to a 17? 16 steps. Right? The mid-range, this is probably, I would say, the most common error in this unit of statistics. And I mean like just in general, and I also mean on a unit test. Right? Because people figure, right, the range is max minus min. Well, the mid-range must be half of that. That's not the case. Right? The mid-range is the average of the max and min, or we could say min plus max divided by 2. So 1 plus 17 divided by 2, 18 divided by 2 is 9. All right? Now it's not terribly far away from what we thought it would be. Like if you thought mid-range, half the range, you would have come up with 8. The real answer is 9. I mean, it's not an end of the world type situation, but it is technically incorrect, and that would cost you. Right? So on the next page we have outliers. Outliers is an interesting topic because depending on the type of data that you're working with, the context of the data, you may come up with something that is a mathematical outlier, but not actually a contextual outlier. Right? An outlier is really just kind of one of those self-defining terms. Like if something is an outlier, it lies outside of what is typical. Right? So if I'm talking about grades on a test, and I'm normally an A student, and I just got a 60 on a test, I would be thinking, all right, that's probably an outlier, right? It could also be unusual. That's another statistical term that we use. But for now, we'll just focus on the outliers, right? So what we have to do, well, there's a couple of ways to handle it. I'll show you the by hand way first, and then I'll show you the calculator way, and I'll let you decide which you like better, right? Any value that falls outside the range of LQ, right? LQ is the lower quartile, minus 1.5 times the IQR, which is the interquartile range. I'm going to write all this down in a minute, comma UQ, upper quartile, plus 1.5 the IQR, right? So LQ is equal to lower quartile UQ is equal to upper quartile the LQ is also known as Q1. The UQ is also known as Q3. The Q representing quartile, and the subscript representing which quartile it is. So the lower quartile is also known as the first quartile, right? Upper quartile is also known as the third quartile, right? What they are cutoffs. So we could break data into quarters, right? So we can group it so that the lower 25% of the data is together, the second group of 25%, the next group of 25%, and then the upper group of 25%. These values are the cutoffs of what constitutes the lower, middle, and upper quartiles. Right? The IQR, interquartile range, is equal to Q3 minus Q1. All right. Interquartile range is equal to Q3 minus Q1. So if you find the upper quartile, subtract from it the lower quartile, and you have the interquartile range. All right. So the way to find, manually, the way to find the quartile values is first find the median, right? So I'd look at my data set and I count inward. Now, it's already in increasing order, so it's slightly better than the problems on the previous page, right? So I'm going to count inward until I'm left with only one or two values, right? So I'll do what I did before where I move the highlighter over. So it's one step over, one step back, one step forward, one step back, forward, back, and then they both eventually land on the 7 in the middle. Right, so that's my median. All right, didn't ask us for that, but I needed to know the location of the median in order to figure out the lower quartile, because the lower quartile is the median of the lower half of data. You know, you think about like what is a quarter? It's half of a half. Half of a half is a quarter, right? So I cut the data in half, then I cut it in half again, and that gets me to the quarter-way point, right? So what I'm going to do is I'm really just going to look at this part of the set, everything that's less than the median. And I'm going to find the median of that new mini set of data or subset of data. Go with the yellow here. Let's keep the score going. So I'm going to slide it over, slide it back, and just like one of the problems we did on the previous page, we have two middle numbers. So to find the lower quartile, I need the number directly in between the two numbers that make up that lower quartile. All right, so I'm taking 4, adding to it 5, and dividing by 2. So 4.5. All right, and by the same rationale, I'm going to find the upper quartile. All right, so, oops. So count inward. It's the same breakdown. So there's no reason to think the process would be any different. The 9 and 10 make up the median of this interval, which is the upper quartile. So I find the average of 9 and 10. All right? So 9 plus 10 divided by 2 is going to be 9.5. All right? The median in terms of whole numbers, consecutive numbers, really the only possibility is that it'll be a whole number itself or it'll be a 0.5. But once you get decimals involved, things kind of get a little wacky. But for a simple data set like this, it's not that bad. All right, the interquartile range is 9.5 minus 4.5. Which is 5. (9.5) minus 4.5, which is an even 5, right? Just a word on types of numbers. I mean, it's a stat class. The numbers are going to get ugly fairly frequently. I would say do not expect many problems to work out this cleanly. All right, they're going to be ugly, especially the ones that are contextual based, all right, or context based. So what I'm going to do is I'm going to apply my rule. I'll rewrite it down here: LQ minus 1.5 IQR, comma UQ plus 1.5 IQR. So the LQ is 4.5. The 1.5 is built into it. Oops. We're multiplying that by 5 because that's the IQR. Then we're taking the 9.5 plus 1.5 IQR. So that IQR again is 5. So really, the only things that we're adjusting when we plug into this formula is the lower bound, that lower quartile, I should say, the upper quartile, so the difference between those two, and one gets a minus, one gets a plus. All right, so I'd go back into my home screen just to crunch these numbers, calculate 4.5 minus 1.5 times 5. All right, so that gets me -3. Then 9.5 plus 1.5 times 5, which is 17. All right. The question says determine, or the directive, determine if the following set consists of any outliers. What I just came up with is the interval of non-outliers. The interval of non-outliers. So anything that falls between -3 and 17 inclusive is not going to be considered an outlier. So any of those numbers, if they're in this interval, they're not an outlier, right? But there is one that's not in the interval. If I go across the line there, I see a 2, 4, 5, 6, 7, 8, 9, 10. They all fall between -3 and 17 on the number line. But the 42 is outside of that interval. So therefore, 3 dots in the form of a triangle means therefore 42 is an outlier. All right, but this is what we call a context-less scenario. It's not contextual. All right, because common sense could override this. It all depends on where these numbers came from. All right, so I'll just give you a quick example. I use this one all the time. It's pretty good. Let's say we're talking about a list of data that represents the ages of students at an elementary school. All right, randomly selected students at an elementary school. mathematically it says 42 is an outlier. But I don't know about that 2 now, because in my interval, mathematically it says the 2 is fine, but I don't think I've ever seen a 2-year-old as a student in an elementary class. Now, I suppose it's possible, especially if you involve like a leap year kind of deal, but that 2 is now drawing attention to itself. It could still be right. Maybe the person's on a leap year, they're a leap year baby, so 2 years means what, 8? So they're actually 8 years old, but they say 2 because it's fun to say that. That's a possibility, but I'm now looking at, I was already looking at the 42 as being, like, that was a little out there. I suspect it's an outlier. But now my attention is drawn to the number 2 because that seems to be incorrect. Now, the difference between, just a kind of a practical definition, difference between something that's unusual and something that's an outlier really shouldn't be there. Like, if you look at that number, there's something about it that says, you know what, I think this might be a mistake, or it's just such an extreme outcome that it's likely out of the ordinary. It's not something that we would consider part of our data set because it's so rare. All right? So that would be like the 42-year-old student in an elementary school class. Right? Now, if this is actually real data that was collected from an elementary school, my guess is 40-year-old teacher brought in their 2-year-old kid, and they counted themselves as part of the data set. But there has to be an explanation for it, because it's so far away from the other numbers that it draws attention to itself. One quick side example. Let's say you have a data set that consists of the numbers 1, 1, 2, 3, 56, and 7. All right. Now you could run an outlier formula on this, like what we just did. I don't want to waste your time doing that. But if I'm looking at this data critically, so again, I'll put some commas there so you know the demarcation. That 56 kind of stands out. I'm looking at a 1, 1, 2, 3, and a 7, and then slapped right in there is a 56. I don't really need a calculator to figure out that 56 is an outlier. 56, I wrote 57. 56 is an outlier. But is it inappropriate to have in the data set? Well, in its current form, sure. But the way that the rest of the data is organized, 1, 1, 2, 3, then 56, then 7, it's increasing in every other aspect. So the likely outcome here, or the reasoning anyway, is that a person probably forgot to put a comma between the 5 and the 6. Like on data entry, they typed 1, enter, 1, enter, 2, enter, 3, enter, then type 56, and then hit. I do it all the time when I enter data. You do it quick. Sometimes you just forget to hit enter, and a 56 could end up in there instead of a 5 followed by a 6, because now the data set makes sense. All right, so there is an explanation. Was probably supposed to be five and 6. All right, so this is an instance where you would not remove a value from a data set simply because it looks out of the ordinary. There was an explanation for it. But this other one, without the context, we don't really know. So we would just leave it in. But what we typically do when we do statistical analysis, if we suspect that there's an outlier, we just end up doubling the amount of work that we have to do. Because there's an outlier there, so now I have to run the data, create graphs, find summary statistics, draw conclusions with the outlier included and with the outlier removed, and present both of those sets of findings. Right? Alternatively, if you could flesh out that there was a mistake in there, you could save yourself the time and energy, but aside from that, you'd have to recollect the data and start over. All right, so if you expect or suspect that there was a flaw in the data entry process, that could be an issue. All right.
So really quick, sorry.
Sure.
So the 42 is the outlier because it's not between the -3 and the 17?
Exactly.
I have a question as well. Whenever you give like an outlier question, will you always have the equation there for us, or we have to remember that?
You'll have to know that.
Okay.
All right, now that being said, that kind of brings me to the next part of this. There is a way to determine outliers using a statistical graph. All right, either way, it's something you have to remember, but maybe this is more to your liking because there's a lot of writing here. I mean, even if you streamlined it and took away all the little notes I threw in, it's still a fair amount of stuff to write for not really that much of a payoff. All right, so we're gonna go into, and this will be the last thing that we do for tonight, because it kind of has to be. I'm gonna hit the home button. I'm gonna go to statistics. All right, so exactly what we did before. I'm gonna wipe out the data that I have here. So again, we wipe it out by hitting the backspace and then confirming it. All right, there's other ways to do it, but that's I found to be the most efficient. We type in our new data, 2, enter, 4, enter, 5, enter. Alright, so I put all those values in, can't actually see them all at the same time, but remember, it's gonna populate in the frequency column, it's gonna populate ones, because I typed in that 2, I typed that in once. That 4, I typed it in once. The 5, I typed it in once. If I type in something more than once, I could actually, instead of, like if the number 5 repeats like 7 times, instead of typing 555 down the line, I could type in the 5 once and put whatever the frequency is, like 7 times, I'd put a 7 in the frequency column, right? Now, for this one, so let me jot it down over here. You go to statistics, you select graph, so all the way up to the top. In some displays, you can hit the up arrow and get all the way to the top. Some you can't. You'll get kind of locked right here, and you keep hitting the up arrow, you're not going anywhere. That's where you hit that little curly back arrow. That'll always bring you right to the top. Just don't hit it more than once, because that'll bring you back to the home screen, which would then bring you back to, well, the top of the home screen. Right arrow to graph. Okay. We have a few choices here. We're going to kind of live with the first two for the majority of the course. But in this case, I want the box plot. And we'll talk about how you actually graph box plots, on paper, because we'll need to know that. But for now, I'm just going to say this technique will help you identify outliers. All right, so I'm going to hit box plot, okay, and your graph may not look exactly like this, because I have a setting that's selected, and I'm going to tell you to select that also. So if you go to settings, you'll see an option for display outliers. Turn on display outliers. All right, so you turn on display outliers. I have mine on already. So I'll turn it off for a second just so you see. When you look at the graph, prior to doing that, this is what the box plot would look like. Okay, if you're not familiar with box plots, this is like uncharted territory. But if you've seen box plots before, you know this is what a typical one looks like. Right? But by putting on outliers, or display outliers, it's going to remove from the body of the box plot any outliers, any loose point that you see. See the whole bulk of the box plot's all smushed over here, and then you have this loose point just hanging out over here. Any loose points that are just kind of hanging out off the beaten path of the graph, those would be outliers. So unless, in this case the data set's pretty clear. Like that must be the 42, because everything else is 2 through 10. and then you have that 42. So it's like you go into it suspecting that the 42 is an outlier. The fact that it's a disjointed point means that it is confirmed as an outlier. All right, but maybe it's not so obvious. Right? If that's the case, just hit the right arrow until that little orange cursor thing gets over to the point, and at the bottom of the screen, it's going to tell you what that value is. It says maximum 42. Right? It'll also tell you the other values here. This is related to what we just figured out with the quartiles. The lower quartile, median, and upper quartile. This graph also tells you that stuff too. Right? So it gives me the minimum, which was easy enough to find. 2 is the smallest number. But then it'll tell me the first quartile, which is why I introduced the different terms. You have lower quartile, first quartile, Q1, they all mean the same thing. Right? So in this display, it writes it as first quartile, 4.5. That's what we came up with. Median, 7. We came up with that earlier. Upper quartile, 9.5. And then what the maximum would be if the outlier is removed. Right? They call it the upper whisker. Right? It's a reasonable enough name, I guess, for something that sounds silly to begin with. Because box plot is also known as a box whisker plot. Right? So the box part of it makes sense, but those little tails that, I can't even zoom in on it, but those little tails here, you see there's a little guy over there and a really little guy over there, those they call whiskers. Right? So if I turn off my outliers, so you have a very small whisker on the left, but a really lengthy one on the right, but by removing the outlier, I have I don't want to say it's roughly symmetrical. It's still got a little bit of skew to it, but it's definitely more compact than it was previously. All right, so that's a way that you can get outliers without having to do this stuff, but it requires data entry, making sure you're in the right setting in the graph, box plot, display outliers. So, you decide what the trade-off is and whether it's worth it. All right. So yeah, let me stop the recording here. So we're going to look at frequency tables and how to find the mean, median, mode, range, and mid-range. All right, so I have an example here where I'm going to just take you through it by hand just to give you the experience, but we're almost always exclusively going to do it on the calculator. All right, so this formula tells us to take the sum of the product of all the x and f values. So these are my x values, these are my f values. I'm going to find the sum of that product. So I'm going to multiply across in each case, and that's going to populate the x times f column. So I'm going to get 1 times 10 is 10, 2 times 3 is 6, 3 times 1 is 3, 4 times 8 is 32, 5 times 5 is 25. All right, I'm going to add all these up. So 16, 10 plus 6, 16, 19, 51, 76. All right, and then I'm also, so that gives the numerator 76. The denominator is what I would get if I added up all these values. So 10 plus 3, 14, 15 if I add the 1, 23 if I add the 8, and 28. So 76 over 28. I'll just go into my ordinary calculator here. 76 divided by 28 is 2.714. And so that would be the mean of this frequency distribution. But let's do a double check by putting it into the statistics app. I'm going to wipe out the data I have here. All right, so 1, 2, 3, 4, and 5. Then instead of the ones, I want 10, 3, I got the 1, 8, and 5. So I'm just going to run up and over, all the way up, all the way over, hit OK, and go down to the one that is an X bar. And I get something different. Okay, where did I go wrong? So it looks like I typed the data incorrectly. Unfortunately, simple addition eluded me. So this should be 27 So 2.814. And that would be our mean. All right. You could also use it to find the median. The median here is going to be 3, but I just wanted to take a minute and talk to you how you would do it by hand. Talk to you about how you do it by hand. So what we do, there's actually a couple of different ways to do it. Cancel frequencies associated with the lowest value in the set with the highest until you come against 1 or 2 values remaining. Those make up the median. All right, so I have 5 5s on the high side. I can cancel 5 of these with 5 of these. If I do that, I'm still left with the other 5. So I'm basically canceling all 5 of the 5s with 5 of the 10 1s. All right. Then I'm going to cancel all 5 of the 1s with 5 of the 8 4s. Always working my way inside. All right. Then I would cancel these 3 values with these 3 values, and I would be left with 1 value in the middle. All right, that's telling me it's not the median that's 1, it's that 1 value that is the median, in this case the number 3. So the median is equal to 3. All right, so it can be easy enough to do it in the calculator, but if you don't have the calculator handy, you could try this cancellation technique. All right, the mode is the most common value. So here I'm looking at, the 1 occurs 10 times, so the mode is 10. If I scroll down the line here, it tells me that the mode is 10. The mode is 1. It occurs 10 times. All right, so the mode is 1, and the mode frequency, how many times it occurs, is 10. All right. Sometimes you're given an interval. If you're given an interval, you want to find the class midpoint. So I want to average. I'll just make a little note here. Average AVG of 10 and 19. All right. And then I would do the same thing for 20, 29, 30 to 39, 40 to 49, and so on. All right. So if I average 10 and 19, I get 14.5. If I average 20 and 29, I get 24.5, then 34.5, 44.5, and 54.5. All right, so I go back into data. I could wipe out all this stuff, confirm, and then pop in the 14.5, 24.5, 34.5, 44.5, and 54.5. Then I have my frequencies: 51, 13, 22, 4, and 92. All right, so it's saying find the mean, median, and mode. Well, I can't really tell what the mode would be. I can't tell which value occurs most frequently. All right, so what we'll do for that is we'll get a modal interval. And for the mean and the median, we're going to approximate those. Well, the median, I can get an interval out of it, but it'll still be an approximate. All right, and if I try to nail it down to a particular number. All right, so up and over, okay, and down. I'll go for the median first because it's right here. So the median, I'll use the abbreviation. Median is approximately 54.5. Go down, find the mean. The mean X bar is approximately 38.511. And the modal interval, I just got through saying that, is, well, the one that occurs most frequently is the 50 to 59. So we indicate that as an interval. All right, so now we're going to talk about measures of variation. So the little statement there, it's just as important to know how spread out the data is as it is to know the central tendencies. So we start off with the sample variance. And in this whole unit, everything is going to be related to a sample. So
We don't have to really worry about anything beyond that at this point. So the sample variance, if it's just a raw set of data, we use this formula. If it's a frequency table, we use this formula. But just like some of the other things we've talked about, I'll give you one example where we do it by hand, and then we'll go over to the calculator. All right, so if you look at this formula, you see that the innermost part of it is x minus x bar. So what I want to do is find x bar, which is the average of these values. All right, so I'll just go to my calculate menu, app I should say. So we have 2 plus 3 plus 6 plus 3 plus 6 plus 8 plus 0. And we're going to divide that by 1, 2, 3, 4, 5, 6, 7 values. So it gets us an even 4. So I'm going to create a new row where I just simply find x minus x bar, which means each of the x values minus the x bar. So I'm looking at, if I just subtract a 4 from each number, a -2, a -1, +2, -1, +2, +4, and -4. Expanding out, we have a power of 2, so I'm going to take these values and raise them to the power of 2. So that's going to give me a 4, a 1, a 4, a 1, a 4, and a couple of 16s. All right. This symbol here means to add those up. So I'm just going to kind of tuck it around here. Just pop in equals plus, 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 plus. And so we get 8, 10, 14, 30, 46. All right. And then this little guy here just means the number of values in the set. All right. Here, n is equal to 7 because there's 1, 2, 3, 4, 5, 6, 7 numbers in the set. So I'm going to take that 46 and divide it by, see, it says n minus 1, so 7 minus 1, so 46 over 6. The standard deviation, which was what they're asking us for, is the square root of that number. So I'll plop that in. We're at 46 divided by 6. And I'm looking at about 2.769. Now, standard deviation is actually a comparative value. If the standard deviation is equal to 0, that means all the values are the same. If it's bigger than 0, it means that the values are not all the same, but we don't know in what capacity until we have something else to compare it with. So I'm just going to take a minute and pop all this into, or for number 2, pop it into the calculator and pull that standard deviation. And we'll see what the relationship is between the data in example 2 and example 1. So 10, 20, 35, 41, 52, 11, 14, 1, 3, and 8. All right, so up and over, okay and down, and sample standard deviation here. All right, so, oh, they wanted variance too, so let me get that. S squared is the variance, 263.441, and S, which is our standard deviation, 16.231. All right, so you can see this number is much larger than that one, and that corresponds with this data set being way more dispersed. All right. The lowest value in this data set is 10, the highest is 52, the lowest in this one is 0, and the highest is 8. So definitely a higher degree of dispersion there.
Early in my career, it's a little bit more of a, let's do it by hand. Why? Because that's how I learned it. Now it's more like, let's do it by hand, but only if it serves a purpose. I just realized I got to change the date and time on my iPad. Anyway, measures of position. this refers to standard deviation, right? So measures of position we make those determinations based off of our knowledge of standard deviations, right? So every score can be represented in terms of standard deviations away from the mean, right? So what we think of when we're talking about relative positioning or the position of an entry within a data set is how many standard deviations that value is away from the mean, right? So if I tell you that, for example, just a quick one, if I tell you that the mean is 0 and the standard deviation is 1, what I'm saying is that this ruler would be measured in terms of those standard deviations. And so we would establish, like which tick marks mean what. But I would say, for example, if I wanted it to be centered around 0, that each little tick mark, regardless of size, would be measured in 1 unit increments. I could do that way. But if you're really kind of treating it like a ruler, then you would say something more like, I'll write this back in a second, but I'll just show you real quick. Like if I wanted to call this 1 unit, then this would be 1/8 of a unit and so on. That's more of a traditional ruler representation. But I'm saying that each little space here, so this little guy would be measured in 1 unit increments, all right? But just like in a function related math class, whether it's college algebra or pre-calc or whatever, anything basically not statistics that we offer, you could also have negative numbers, right? So this is in the positive direction. We think in terms of steps. So I'm taking 1, 2, 3, 4, 5, all the way up to 8 steps in the positive direction, but I could also go in the negative direction. So 1, 2, 3, 4, 5, 6, 7, 8 steps. So I label that -1, -2, -3, -4, -5, -6, -7, -8. All right. So if I were to compute a standard deviation for a simple data set and determine that that value is equal to 2.769, and then find the standard deviation of a completely different sample of data and determine that that sample standard deviation is 4.559, I have now a basis by which I can measure the two against each other. All right. So what this is saying is, instead of having, I'll just look at example 1 again. Instead of having each increment be 1 unit, I have a mean of 4 here with a standard deviation of 2.769. So again, going back to example 1, instead of being centered around 0, I'm now centered around 4. And each one of these little tick marks here would be, instead of 1 unit to the right, this one would be, it's going to be tough to write it in here, but I'll use a little arrow. This one here is going to be 4 plus 2.769. All right, because I'm starting off with the mean and adding to it 1 standard deviation. All right, so that's what this represents. Previously, over here, the mean was 0 and the standard deviation was 1. So that 1 that I first labeled here, that was 0 plus 1. the mean plus 1 standard deviation. It's the same action, it's just using 2 different values. Instead of 0 and 1, it's 4 and 2.769, right? So you can see how this will get pretty out of hand pretty quickly, because the next one would be 4 plus 2 of those 2.769s. That's the same as saying X bar plus 2 times whatever the standard deviation is. All right, so it gets a little messy, or very messy, very quickly. But the same concept is at work. All right, we could also go the other way. So for example, if I wanted to go to this location here, that's 3 steps to the left. So 1, 2, 3 steps. This one would be the same as saying 4 minus 3 of those standard deviations of 2.769. That's the same as saying X bar minus 3S. All right, very strange, but very useful, because the scale makes or allows you to make a determination of spacing. All right, so if I tell you in this data set, I have a number like 10, how far is that away from the mean? You can count in increments of 2.769 away from 4 and come up with that value. All right. You could also, I mean, you could do it using technology also, you know, just to get an idea, and then you'd figure out what the placement is. So if I did it using technology, I would just keep it simple. I would have 4 plus 1 times 2.769. It helps if I hit the right button. 769, right? So 1 unit away would be 6.769. And then I would just do that again, replacing the 1 with a 2, replacing the 1 with a 3, and so on. And that would give me all the individual measures that are associated with the ruler, right? It can be a little much. We don't want to have to label out an entire ruler with new metrics. So we just think of it in terms of standard deviations, because the underlying principle would be the same. You would just be changing the values along the way. There's other little shortcuts in Desmos that'll get us there, but that's the gist of this idea of measure of position. What we would do is establish the location of a number within our ruler and then use that to compare to another ruler, right? And we'll see more of that. There's shortcuts. There's plenty of easy ways of doing it. It's just not always the most user-friendly thing in the early goings. All right. So that brings us to something called the empirical rule. The empirical rule is really important because we can use that to make a determination of whether a distribution is considered to be normal. Right. So a normal distribution is a symmetric curve, bell-shaped. I mean, that's the best I can draw it. So pretend that's symmetrical. I'll try it again. I always like to give it a couple of shots before I give up completely. All right, that really is the best I can draw it. I know it doesn't look perfectly symmetrical, even slightly symmetrical, but that's what a normal distribution looks like. And so if about 68% of the data lies within 1 standard deviation and about 95% lie within 2 standard deviations of the mean, and about 99.7% of the data lies within 3 standard deviations of the mean, then we would say the distribution is considered to be normal. All right. So what that means is that we have to establish our ruler based off of this idea, but the ruler is just going to be along the x-axis. All right. So the way we label up a normal graph, normal distribution graph, is by placing X bar right in the middle and then counting out 3 steps in each direction. All right. that first part of the ruler would be X bar plus 1s. The second tick would be X bar plus 2s, and then X bar plus 3s. X bar being the sample mean, and S being the sample standard deviation. I try to make my my S's look really S-y rather than really 5E. Yeah, it's very easy to mess up your understanding of a concept based off of the way you write something. Because I've had plenty of instances where people would ask, right, I understand everything else, but where did the 15 come from? Where did the 25 and 35 come from? So, just little things like that, based off of just something as simple as penmanship could be an issue. So just take care of that. So X bar minus 1s, poor quality S, right on cue. X bar minus 2s, and X bar minus 3s. That one really looks like a 5. All right. So what this rule, this empirical rule is saying is if in this region of the graph, you have about 68% of the data. This is how I know it's not really symmetrical. This other part of it should have been like over here. Again, it's not an art class, so not overly concerned, but it'd be nice, a little bit better. So about 68% of the data should be in this region. All right. Then the second region should contain about 95%. And then the last range, the last interval should contain about 99.7, which is oddly specific. Because like about 99.7 isn't 99.7 pretty exact to begin with, but that's the rule. So about 99.7% would be in this interval. And you don't have to tolerate my crappy drawings. This is something you very easily find with a quick Google search. So normal distribution or normal curve, and a lot more creative people out there than me, and they come up with nice ways of visualizing it. All right, but yeah, these percentages, this is what we're looking at. If we can establish these percentages to be true based off of this graph and the data that corresponds to it, then we would be looking at something that's considered to be normal, or a normal distribution. To the cloud. That's out of the way right now. And yeah, like I said, we're gonna tackle this problem again. This time we'll start off with the NumWorks calculator. Right. So the question, the problem, the concern was to use the empirical rule to determine whether the following data follow a normal distribution. It feels like a typo. Follows. Anyway, I'll let you be the judge of that, because obviously grammar is not my strong point. So what we're going to do, if we're using NumWorks, all right, so this screen is I'm using the app, so it's a little nicer, but we're going to, it's touchscreen. So I'm going to go into statistics. So I hit the home button. So I'll just jot it down here for NumWorks. You're going to hit home. I can't draw the picture of the house, so I'm just writing home. Statistics. All right. So I can hit OK or enter on statistics. And it brings me to my data editor. Now, this is information I had from another class. So you're going to run into that scenario. Anytime you use a calculator, if you use it for something else before that, you might have information that's in the way. All right, so to clear the list, we go, so I'll say to clear the list, go to value V1 and hit enter, and hit OK or enter. I'll make this look more like a 1. Value V1 and hit OK. All right. So right onto the red and hit OK. And you'll see an option that says clear table V1N1. That's what we want. So we go to clear table. All right, and I'll explain what the N1 part of it means in a second. But in this list, you can see that it also gives you an option to display a column for cumulative frequencies if that ends up being an issue. Right, but I just want to clear this table. It'll ask me, do I really want to do it? Some other calculators don't do that, and you're searching for the undo button. This one's asking you, do you really want to delete the stuff that's in the list? Yes, I do. So it's gone. All right, now I'm just going to type in my values. You start off with the X list. So 14, 16, 18, 20, 22, and 24. All right. And you'll notice that it automatically puts frequency values of 1 in for each of these numbers, because it assumes that you only want that number to show up once. But I don't actually want it to only show up once. I want it to show up more than once. So, well, the first one I want to show up once. The second one, I want to show up 7 times. So that 16 occurs 7 times. 18 occurs 14 times. 20 occurs 13 times. 22 occurs 5 times. And 24 only occurs once. All right, so I can leave that one alone. All right, so I have my data in. If you remember from last class, I know it was a week ago, so maybe not, we're really looking for 2 pieces of information. We're looking for the mean, so the sample mean, which is X bar, and the sample standard deviation, which is S. All right, so to get these values, so these 2 values, we go to stats. All right, so we go right up the line here until we're in the column heading areas and go right to stats and then hit OK or enter. And we have a ton of information. They give you everything. They give you everything that they think is relevant. All right, but we want to go down the line till we find the one that says sample mean, which is 18.82927. But if we're rounding to 3 significant digits, it's 18.829. And the sample standard deviation S, 2.144 if we're rounding to 3 significant digits. All right, so that's the sample mean and sample standard deviation. Now, I'll show you in a couple of minutes how to do it on Desmos, but for now, I'm just going to say that's all we need really any kind of special type of calculator for. Everything else is just rote number crunching. All right, so I'm going to compute based off of this rule here, X bar plus or minus 1 standard deviation. And so the way that is, I'll leave it over here for now. X bar minus 1 times the standard deviation, and X bar plus 1 times the standard deviation. All right, that's our first computation. Then once we've completed that computation, we're going to do, if necessary, we're going to do it 2 more times, but this time with 2 times the square root of nothing, 2 times S. And then 3 times S.
All right. So those are our 3 sets of computations. Now, the issue that we run into is that that's a lot of typing if you don't use technology to its fullest advantage. So I'm going to go back into my home screen. All right. So I'm going to hit that home icon. If you're ever in doubt and you're like, where should I go from here? Odds are you're going to go home and just kind of recalibrate. Well, what do we want to do? We want to make some calculations. So I go into the calculation menu, hit OK. I have other stuff from another class here, but I can start doing my computations because I know what X bar is. And I know what S is. So everywhere in these formulas that I have an X bar, I'm going to replace it with 18.829. And everywhere I have an S, I'm going to replace it with a 2.144. You don't actually have to show the substitution. That's just writing for the sake of writing. You could just go right to the bounds. All right. So what I mean by that is I'm going to run this computation here. Let me make that look a little nicer. This computation here, then this computation, this one, this one, this one, this one, and put our results right below it. All right. So X bar, which is 18.829, minus 1S. So 1 times S. So 1 times 2.144. All right. That's going to be my first computation, which gives me a 16.685. All right, so that result goes right here. Then I move on to the next computation where I take it's the same X bar and the same S, except now I'm gonna be adding instead of subtracting. So I'll hit my up arrow. And I'm going to recall this previous computation once I highlight the thing that I want. I mean, if I wanted this one, I'd go up there. If I want that, I'll go there. You just toggle back and forth until you get what you're looking for, and then hit either OK or enter. It brings it, I'm sorry, OK or execute. It brings you to the bottom of the screen where you can make edits. All right, so I'm going to go over here and change that minus to a plus. All right. And then I'm going to hit execute or OK, and I'm going to get 20.973. Oops, 20.973. For the sake of learning the skill, I'm not going to account for any percentages yet. I'm just going to go right across the line here and just keep running computations. So up arrow, go back to the one that has a minus. I need this, really this structure, but that one needs to be a 2. All right, so X bar minus 2 times the standard deviation. So my low bound is going to be 14.541. Just go up, change the minus to a plus. And I get my upper bound, 23.117. Right. So all I'm doing is changing 1s to 2s to 3s. Now we're doing the 3s. So I grab the one with the minus, change the 2 to a 3. Oops, that's not a 3. And I get 12.397. My upper bound I'll get by changing that minus to a plus. 25.261. All right. So these are the 3 regions of interest. The first one gives us 1 standard deviation away from the mean. The second gives us 2 standard deviations away from the mean. And the third gives us 3 standard deviations away from the mean. Right. So what I want to do, just looking at this column here, the X values, I just want to take note of which ones
fall between these two numbers. All right. So in this case, just get rid of that for a sec. I can tell you that 14 is not big enough. It's got to be between 16.685 and 20 point, well, I'll just say 16.7-ish and 20.9-ish. All right. 14 is not there. 16 doesn't quite make it. 18 falls between those two numbers. 20 does, barely, but it does. 22 does not. Neither does 24. So the only two numbers that are relevant here would be 18 and 20, but we have to remind ourselves that the 18 occurs 14 times and the 20 occurs 13 times. All right, so that's a total of 27 values. There's a total of 41 values in the entire data set. We get that by adding these numbers up. So 1 plus 7 is 8, plus 14 is 22, plus 13 is 35, plus 5 is 40, plus 1 is 41. All right, so a total of 41 values in the data set. All right, that's just adding them up. So I'd want to see about what percentage this is. All right, so 27 divided by 41 is in the neighborhood of 66%. It's just a smidge short, but if I wanted to put this as a percentage, I would say about 66%, but this number corresponds to point, if we're rounding appropriately, 658, which in turn is about 66% if we're going to the nearest whole number. But if we're not going to the nearest whole number, then we would leave it at 65.8%. And you'd say, well, it's not quite close enough, because we defined approximately to be about 2 percentage points. All right, so it's right on the border. Right? It's close to 68%. We want it to be 68%. It's close, but it's not quite there. Right? So we'll let the rest of the data kind of decide for us. I'm sorry, the rest of the computations decide for us whether the data set follows a normal distribution. All right, so looking at the second interval of values. So we know that the first interval contains the 18 and the 20. 14 is still too small, right? This goes from about 14 and a half to a little bit more than 23. 14 is too small. 16 is fine now. 18 is good, 20 is good, 22 is good, but now 24, well, not now, but 24 still doesn't fall in the interval. All right, so my second set of computations gives us this region. All right, the numbers 16, 18, 20, and 22. All right, but really we're focused on how many each number occur, or how many times each number occurs. Here I can say that, well, it's 12 more times than the previous interval, because I now have a +7 and a +5. All right, so that gets me up to 39. Yeah, 39. So 39 out of 41.
I have a question. Where did you get the 41?
The 41 is the total of the values in the set, if you add up the frequency column. All right, so we're looking at 0.951, all right, which does round to 95%. All right, so what we're looking at here is something that was kind of on the borderline for the first interval, but for the second interval, it's right at the target number, the 95%. Right, so now we're just going to investigate the last case, which is going from about 12.4 to about 25.3. Right, every one of the values falls in that interval. Right, every one of these numbers here, let me just do this real quick and then zoom back out. Every one of them falls in the interval. So if I account for every one of the values there are 41 values overall, but all 41 of them fall in this interval. All right, and again, just by taking the numbers, I'll just do it on the screen here. 1 plus 7 plus 14. I missed a 7 plus 14 plus 13 plus 5 plus 1, total of 41 values. I'll show you another way you can get that in a minute, but this would give us, well, there's no need to go to decimal form here because it's going to give us an even 100%, which is definitely within 2 percentage points of 99.7. All right. So we actually never say something is a normal distribution. We say that it follows a normal distribution. All right. So it has this same structure and roughly the same percentage values as a normal distribution, but it does not ever have to be exact. So what I would say as a conclusion here, which is the opposite of the conclusion when I had that snafu last time, is the data follows a normal distribution. All right. But again, you might put a little asterisk on this one here because it rounded to 66%. It was pretty close. Another person could come along and say, well, it's not by the book. It's not exactly 2 percentage points away from 68%, so it's out. But we do allow for gray area. All right. So it's very, very close. So we're going to let it slide basically. And just think about it like if you put an answer to a question on a test and maybe you didn't get the notation exactly 100% correct, but I could look at it and say, oh, but you're so close. I'm going to let it slide. I'll give you full credit. Right. It's along those lines.
I have a question.
Yes.
Hi. So the first one, are you big on the approximation sign, especially when you're dealing with the decimals?
It's not really necessary. I mean, if it occurs to you to put it in, but I'm not going to be looking to take off credit if it's not there.
Oh, thank you. And the next question is, based on the data set for the middle and the last one, which is like 95% and 100%, is it because both of those fall within like higher than 95% or 95% and over 100%? Does that mean that it follows the data set?
Yeah, so
distribution?
because it's right at 95% and it's so very close to 99.7%, we would say the first category is pretty close, the second category is spot on, and the last category is very, very close. So if you can meet those 3 criteria, then you would say the data follows a normal distribution.
Thank you.
No problem. All right. So just very quickly, let me bring up Desmos here. That's not Desmos. Actually, I don't even remember doing that. So let me go to Desmos, learn together. And the calculator that we used was measures of center and spread. All right, so this one, again, it was for a single list of data for a frequency distribution. Really, the only thing we need a calculator for, a special kind of calculator, like I said before, is for the mean and standard deviation. All right, so in the Desmos calculator, I type in my X values, just like I did in the NumWorks, 14, 16, 18, 20. Oh, it assumed what I wanted, so I should have just let it go. And then my frequency values 1, 7, 14, 13, 5, and 1. All right. So this is not a single list of data. It's a frequency distribution. So I'd hit the little drop down there. It'd give me the sample mean of 18.829. And it'll give me the sample standard deviation of 2.1. Well, it should be 4.4. So even this is not working. Oh, wait, no. You know what? welcome to the world of me. I don't think I'll ever create something in which there isn't a typo. So the Desmos calculator that's stored on Brightspace, I have to make one final adjustment. It should be -1 on the bottom, but it will give you the 1.44. I'm sorry, 2.144 when I'm done whipping it into shape, because it needs a little bit more tweaking. But really, this is all you need. And then from there, you do the number crunching just the way we did here. You take your numbers 18.829 minus, I'm not going to do each one of them again, but I'll just do one of them just so you see, 2.144, and you'll get your 16.685. Now, the thing about Desmos that's a little bit different, I mean, it's different from everything else, but noticeably different, is that, I mean, you could use a mouse or a trackpad and copy paste from one field to another, or you can hit that little gear icon and that double piece of paper icon there, just tap on that, it'll duplicate, and you can just make a quick adjustment. All right. So, you know, there's pros and cons either way. You know, in the end, I wouldn't begrudge you if you said, you know what, I'll just use both of them. You know, I'll use NumWorks for this and I'll use Desmos for that. You know, I leave that part of things up to you. All right. But the next example talks about really the same thing, but now it gives you a little bit of context. Data below is a distribution of the ratings of teaching effectiveness for the students in a large introduction to psychology class. There are 400 students in the class. The questionnaire provides students with 15 statements, and the student is asked to pick a number between 1 and 5 that indicates the degree to which they agree or disagree with each statement. One of these statements is the instructor in the class or course is outstanding. A response of 5 indicates that they agree with it fully, and a response of 0 means that the student disagrees with the statement completely. Personally, I think 0 should be disagrees completely, but you know, that it wasn't my study. All right. So we want to visually determine whether the following is a normal distribution. All right. So looking at the previous example, a normal distribution, first and foremost, needs to be symmetric. All right. It doesn't have to be exactly symmetric. It should be roughly symmetric, with the smallest frequency values associated with the most extreme X value. So the smallest X value should have the smallest frequency value. The largest X value should also have one of those smaller frequency values. All right. If it's not symmetric, I would not think that it's a normal distribution. All right. And so what we're looking at here, and first off, the X values are in reverse order. So kind of like a little trick question here, but the calculators aren't going to fall for it. So it's fine. All right. But they are in order. And I'm looking at, in the top value here, I have a 150, bottom value, I have a 5. That doesn't seem very symmetric. These two numbers should be in the same neighborhood. These two numbers should be in the same neighborhood. All right. If they're not, it's probably not a normal distribution. All right. But it is possible that they jumble up the X values so crazily that you don't realize, oh, it is symmetric. It's just if I put it in order, I'd see that. All right. So let me go to NumWorks. Let me go to NumWorks. There we go. We're gonna go home. So it's the same process. All right. So that's the good news. Bad news is it's still kind of a process. So okay on calculate. Oh wait, no, we're not there yet. What am I doing? Statistics. We want to put fresh new data in here. Now you can overwrite data values. So I'm going to hit okay on data. I can overwrite these values and delete what I don't want, or I could just wipe it all out in one shot. There's pros and cons either way, but the most notable pro to not wiping it out is if the data you're typing in is just a minor adjustment from a previous data set, you might just want to overwrite some of the values, not all of them. All right. But this is completely different. So I'm going to go right up to V1, hit OK, and clear the table. It'll say confirm, I confirm, and now we have a blank slate. All right. Alternatively, I mean, I suppose you could just reset the whole calculator, but the thing is that really only works with handhelds, right? So handhelds you got to pay for, these are free. We're just going to be overwriting values or deleting them as we go, right? So I'm going to type in 5, 4, 3, 2, 1. And then again, like I said before, it auto populates the frequency values. Instead of 1 all the way down, I want 150, not 151, 150, 200, 40, and a couple of 5s. All right. So my data's in. I always do a quick double check just to make sure. I mean, there's no reason why you wouldn't want to double check your information. I mean, as we go forward, we're going to find that really the only way we can screw some of these things up would be by typing the data in incorrectly. So we just want to be careful about that, right? But once you have it in, you go to stats. Now you could make a graph. I mean, if you're not really sure about the information, you know, like, is it symmetric? I don't really know. Then you could take a look at the picture, right? It just depends on what picture you want to look at. I recommend a box plot, all right? So you would be able to see symmetry in a box plot if it existed, right? Without even really getting into too much about how to construct the box plot, because that's, you know, not even necessary because the calculator is going to do it. You can take a quick look. Oh, I got to actually be on graph and go to the one that says box plot, and it'll make a box plot. And you just look at it and say, does that look symmetrical? I did alter one setting for another class. Let me just go back. I'll go to the default setting. This is what, as a default setting, it should look like. All right. Or look, I mean, comparing it to an ordinary box plot, a box plot should look like, I'll just jot it down up here. There's a whole page later on in the packet that talks about types of graphs and how to interpret them. But just to give you the gist, an ordinary box plot would look something like this. This would be, I'm sorry, a symmetrical box plot. You'd have the box in the middle, the tail's going out, the tail's roughly the same length. They don't have to be exactly the same length. But that's what a symmetrical box plot looks like. This does not look like that. All right. This actually looks like what a box plot would be if this were all the way over here. You know, actually I grabbed onto too much here. If this were like over here, it's lopsided. That's not symmetrical. All right. So you can get a look at the box plot and that'll tell you or give you a sense of the symmetry, but I want to apply the empirical rule. Right. And when I say visually, there's nothing about that that says you must create a graph. I mean, if you could look at the raw data and see that it's not symmetric, then that's good enough. All right. But if I go down the line here to sample mean, which is 4.213. So X bar 4.213. And the S value right below it is 0.771. Right, that's one of the things about the online version of it, you know, like going through a web browser as opposed to the app, is that there isn't the whole like, is that a 0 or is that an 8? You know, there is an option to show the enlarged screen so you can see it pretty easily. So it's another feature I like. But we're going to run through the same computations we did before, X bar plus or minus 1S, 2S, 3S. So it doesn't really change in terms of what you do, it's just what you get and what it means. All right. And so this is how we computationally verify a normal distribution. So I'm going to go into my home screen, go to calculation, and just start crunching numbers. So again, same idea as before. We know what the S is. We know what the X bar is. It's just a matter of, you know, find and replace. So 4.213
minus 1 times the standard deviation of 0.771. So 3.442. Then again, highlight the thing and hit OK and change a minus to a plus. 4.984. Now this time, instead of going through all these other computations, because I suspect that it's not symmetric, and because if it's not symmetric, it can't be a normal distribution. All right, but just because it is symmetric doesn't mean it's a normal distribution. But if it's not symmetric, it cannot be a normal distribution. Right? It's kind of like a logical linguistic gymnastics. So I'm looking at 3.442 as the lower bound of my interval. 1 doesn't fall in that interval, neither does 2. 3 doesn't fall in that interval. Just short, but it's not there. All right. 4 does. 5 misses it by just that much, a smidge. All right. So the only value that falls in this interval here would be the number 4, and that number 4 occurs 2 times. All right. Not 2 times, 200 times. So we have 200 values that satisfy the criteria. Now, we want to sum. We want to know how many there are overall. That's what we did on a previous one. I just didn't show it. 150 plus 200 is 350. Plus 40 is 390. Plus another 5 twice is going to give you 400. Now, that being said, they did tell us that we should be on the lookout for 400 students. All right. So that's kind of noteworthy that you can actually come up with the sum just by, you know, the total number of individuals just by looking at the problem that's given, you know. So 200 out of 400, that's 50%. I mean, you could show the decimal, but it's spot on 50%. Now, the thing about that is that in order to verify a normal distribution, you need to satisfy each of the 3 criteria, this one, and this one. All right. If any one of them fails, it's not a normal distribution. All right. This is not just 2 percentage points away from 68. It's nowhere near 68. All right. So not near 68%, 68%. Therefore, 3 dots in the form of a triangle means therefore. You can write the word, you could write so, comma, or in conclusion, or however you want to write it. I just, symbolic notation. It saves time and energy. All right. Therefore, data does not follow a normal distribution. All right. Data does not follow a normal distribution. All right. So that's, as a student, and actually, honestly, if I'm being fair about it, as a teacher who has to grade students' work, I'm kind of rooting for this situation here. I want the case where it fails and it turns out it's not a normal distribution after like the first step. It's less for you to write and less for me to grade. All right. In this case, there's a lot more work involved, but in terms of what you gain from it, it's more statistically relevant. All right. At least as far as we're concerned. All right. So that's how we verify something's normal distribution. Now, if you know a data set is distributed normally, then we could use, I mean, there's a whole world of probability and other forms of mathematics that come into play where, and I'll say applied math, not theoretical stuff as much, but you can actually do a whole lot of math if you know a distribution is considered normal.
And one of those things is computing z-scores and determining whether values are usual or unusual. But there's actually, most of our third unit in this course is going to be related to normal distributions. All right. So we're going to spend a lot of time learning the structure first in the first couple of units. But then after that, we'll put it to use and actually draw some meaningful conclusions, which is kind of cool. All right. So with that in mind, we have these lovely formulas here. Z is equal to x sub I minus x bar over s, right? Just talking about the structure of that a little bit. The x sub I represents any individual data point. All right. The x bar and the s, that's the same x bar and s that we had up here. That's talking about the mean and the standard deviation for the sample. All right. Now, these two symbols here and here stand for population mean and population standard deviation. All right, population mean, population standard deviation. We're not going to really do anything with that in this unit, but it does follow the same structure as the z-score for a sample. So it's worth bringing up now. Just know that this is more of a unit 2 thing. So this is more in unit 2. All right, so for practical purposes, we can say at this point, we don't have to worry about it right now. All right, but this other formula we do. All right, that's going to be the main component in the next example. Actually, the next 2 examples. All right, so let's dive right in. Michael and Jane are in different math classes. Michael scored a 75 on his math test. Jane scored a 73 on her math test. The mean score in Michael's class was a 73, and standard deviation was 7.2. In Jane's class, the mean was 71 and standard deviation was 6.3. Which of these 2 students scored better relative to their classes? Key term there, relative to their classes. I'll highlight the whole thing. All right. We already know who did better. Michael got a 75, Jane got a 73. All right. One did better than the other, but did one take a harder test? They're in different math classes. Are they even in the same unit? You know, maybe the unit was more challenging. How do we know which one showed more mastery over the content that they were learning? All right. So what we do is we compute the z-score for each one of them. Michael and Jane. We're going to find the z in both cases. Now that z-score, it goes back to that ruler analogy I used last class. It's really saying that we have a data set that has a mean and has a standard deviation, and we have individual scores. What we're trying to figure out is how many standard deviations each value or each relevant value in this case is away from that sample's mean. All right, that's like the kind of mind-bogglingness that statistics sometimes offers. If I tell you that the value is 3 feet, all right, but I want it measured in inches, you'd have to do a unit conversion. You'd have to say, okay, how many inches are in a foot? All right, that's 36 of those inches. All right, you go the other way and say you have a value that is 100 millimeters. All right, how many centimeters would that be? You do a unit conversion and you see that it's 10 centimeters. All right, so you can go either way with it, but the idea is that you're taking one scale and converting it to another. All right, what we're doing here is taking 2 different scales and converting them to a third scale so that they can be compared against each other. All right, by doing a unit conversion in terms of standard deviations. What standard deviation? The standard deviation. Will it always be the same? No, because it's always going to be relevant or relative to the given data set. All right. Procedurally, it really is just a matter of taking Michael's score, 75, subtracting from his score the mean, and dividing by the standard deviation. Then taking Jane's score, subtracting from that score the mean in her class, 71, and dividing by the standard deviation in her class, 6.3. That's the only crunching that you have to do. Interpretation is going to be a big deal though, right? Numerators in both cases are equal to 2, all right? Which means that each one performed 2 points better than the class average. But we want to know in terms of the individual scales, is that a good thing? All right, so I compute 2 divided by 7.2, because 2 on the top, 7.2 on the bottom, 0.278. 2 on the top, 6.3 on the bottom, 0.317. All right. So I'm going to draw a picture of a normal distribution real quick. By creating z-scores, what we do is we standardize it so that the center of the normal curve is equal to 0. All right, so that's the mean. Standardizing reduces, in each case, whatever the deviation was into a standardized value per 1 unit of standard deviation. All right. So if you look at this and kind of think of it as we took this fraction and reduced it, it would become 0.278 over 1. All right. So this is the deviation from 0. And this is the standard deviation. All right. The new standard deviation. I hit delete. If I haven't said it yet, the person who created undo and redo, it should be like knighted. All right. Same idea for this one. This is the same as saying 0.317 over 1. So this is deviation from 0. And this is the new standard deviation. Because we did a unit conversion. All right. So now it becomes an apples to apples comparison. Right? They're on the same scale now. One of them was on the scale of standard deviation 7.2. The other was on a scale of standard deviation 6.3. Now they're both on a scale of standard deviation of 1. All right. So if I go out 1, 2, 3 units in each direction, just like an ordinary number line, I can actually now plot these 2 pieces of information on the same graph. So 0.278, I mean, they're going to be really close, but 0.278, I'll put right here. We'll go with that as 0.278. And then 0.317 is just going to be a smidge to the right. A little too thick there. All right, so one of them is a little bit further to the left than the other. But now we have a basis of comparison. We can look at them together and say, all right, which one's better than the other? Now that's another conversation, because better is not only relative to the data, but it's also relative to context. All right, you just got to ask yourself, are higher numbers better on a math test? score-wise? And the answer should be yes. But then you look at it in terms of, let's say, a golf score, if you play golf. If you don't, you should know that the lower the score you get, the better you performed. Right? And that's because it took fewer strokes for you to get the ball into the hole. If it took a person 100 strokes to get the ball in the hole and it only took me 3, I'm probably a better golfer. Right? So that's the idea there. You just got to look at it and say, okay, is a higher number a better score? All right. So in this case, yes. So we would say Jane performed better relative to her class. I went off the grid there. Better relative to her class. All right. You just got to be careful. I'm going to say careful, the word careful so many times that it becomes exhausting. And in fact, let's make that the word of the day, careful. Instead of kind of leaving it subtle and letting you figure it out, I'm just going to say it this time. Just say that's the word of the day, careful.
I don't remember what was last week's word of the day.
It was potato.
Oh, we didn't really say
was-
it was the word of the day.
Yeah, it was very subtle. I was trying to.
All right.
up on
I missed the boat on that one.
That's all right. We'll get it. We'll get you many more opportunities before it's over. But yeah, so so just spell it out this time. Word of the day is careful. And yeah, you do have to be careful, because if you write down as a final answer here, Jane performed better. Well, no, Jane did not perform better. She got a 73, Michael got a 75. Michael performed better, but relative to her class, she performed better, right? So it's a subtle difference in verbiage, but it makes all the difference. Now, an application of this goes into what we call the usual, unusual values calculation. So we just kind of streamline that and just say unusual values, all right? Any value beyond X bar plus or minus 2S, which is the same computation that we did up here. So I can bring that right on down. This same computation will tell us whether there are any unusual values, all right? This is what we call the usual interval. All right, the usual interval, which means anything that's not in that interval would be unusual, all right? Or if your z-score is less than -2 or greater than +2, the corresponding X value is unusual. All right. If the z-score is less than -2 or greater than +2, the corresponding X value is unusual. And you could use either method where it makes sense to use that method. All right. The problem is sometimes people use one method when they should be using the other. Right. So I have 2 examples here for you. One of them that's tailor-made for one method, and one that's tailor-made for the other. Right. And a little tip, if you see a raw set of data and they're just asking you to determine if there are any unusual values, then you're going to want to use the bracket method, this one here. All right. But I'll take you through them both. First example, given a data set in which the mean is 72 and the standard deviation is 4, is 59 unusual? All right. So we just got to be careful, again, because when you hear words like unusual, sometimes it makes you think that they're asking for your opinion, and they're not. They're asking for the appropriate computation. So you just got to be careful. Yeah, it seems a little out of the ordinary. I thought it looked weird. No, it's not asking for that. All right. So I have the mean 72. I have the sample standard deviation of 4, and I have an X value.
So I'm going to compute Z equals X minus X bar over S, which is in turn going to give me 59 minus 72 over 4. So 59 minus 72, whoop, that's a plus. 59 minus 72, negative 13 over 4. That's going to give us a decimal. Negative 3.25. All right. And so what we get from that is that we're looking at a number that's less than negative 2. Oops, over shrunk it. So Z is less than negative 3.25. I'm sorry, negative 2. It is negative 3.25. Therefore, 59 is unusual. All right. Try to avoid answering a question that isn't asked. You know, if they don't ask you in what way it's unusual, don't throw it in there, because you could make a mistake, and you never want to lose credit for something that you didn't have to put in to begin with. Yeah, 59 is unusually low, but you know, maybe the context makes that like a better number. Maybe it's a golf score situation. So you don't want to go down that road. All right. So the Z value is less than negative 2. So 59, because 59 is what gave us the negative 3.25, 59 is an unusual value based off of the mean and standard deviations of 72 and 4. So you kind of look at it like, let's say a class took a test and the class average was a 72, but you got a 59, hopefully not. Right? You'd say, oh, okay, well, is that really bad? Is that bad, really bad, or terrible? Right? It's unusual on the low side, so you be the judge. You know, if I told you that your score was unusually low, you're probably not feeling too good about that score. Right? But going the other way, unusually high, you're feeling like a champ. Because then it's like, oh, wait, I did so well that my score is considered unusual. That's how well I did. Oh, I like the sound of that. You know, so it's a simplistic example, but that kind of hopefully gets the point across. And so the last one we'll do before we switch over to the tech assignment is number 2, obviously, because it's the last one. The following data can be considered a simple random sample of ages of NFL players as of June 2019. All right, so it's old data, but it still gets the point across. A typo, it should be determine any unusual values, not outliers. We're not doing outliers here. And then explain the meaning in the context of the situation. Don't be alarmed by context, especially if you're not familiar with NFL players, because really all it's saying is just make sure you state the meaning as best you can using the correct units. All right, these are ages of NFL players. So we'll say things like X years old. You know, that's getting across the context, right? But the data has to get popped into the calculator. So home statistics, just going up to the data part of it. Wipe out the data that we have in there. So onto value V1, hit OK, and clear the table, confirm it. The same process we've been using. All right, so again, home to get into statistics, make sure you're in data. And if there's data here, you go to value V1, hit OK, and clear that table. All right, but once it's clear and you got a fresh table ready to go, you can put the numbers in. You could type it in as raw data, or you can make it into a frequency table, because some of them have repeated values, like that 27 occurs 4 times. You could do 27 in one cell and then 4 in the adjacent cell. All right, I leave that up to you. I'm just going to type it in as raw data because it's not really an overly lengthy set. For the 34s. 35, 36, 44, and 46. All right, I think I got them all in. Find out in a sec. I mean, just taking a quick look at the data though, before you really get started on any computation, you might say, I suspect 44 and 46 are unusual. Maybe the 22. The 22 seems a little low, but the 44 and the 46 seem really high in comparison to the rest of the data. All right, so you make a prediction about what you think is going to be the outcome, but then we get into the nitty gritty, or down to the nitty gritty, over two stats, and we grab the mean, sample mean, and it even has a little notation there. I mean, you really can't beat that. The sample mean is 31.25, so X bar 31.25, and S, sample standard deviation, is 6.340. All right. So I just want to do, because I don't want to go to the Z-score route here, because then I'd have to compute a Z-score for every number that I suspect is an unusual value. I don't like the sound of that. I'd rather do X bar minus 2S, X bar plus 2S.
Why did you choose to do it with the 2S, not just because that, oh, okay, gotcha. Sorry.
No, it's all good. Yeah, sometimes it's just a rule, right? But when we get into the probability unit, we'll start to see that a lot of the rules that we learn kind of evolve from certain probability principles. This one's a little simpler in that if this interval contains 95% of the data, then anything that falls outside of that interval would have to occur less than 5% of the time. So we're basically saying that anything that occurs less than 5% of the time, we're going to say that that's unusual. All right. So, like if somebody said that there's a 5% chance of rain tomorrow, and you walked outside in the morning and it was driving rain, it was going sideways, trees leaned over and everything, like you'd be like, oh, I didn't see that coming. That's kind of unusual based off of what the report said. All right. So that's the same idea here. So we go to calculation, home calculation, and then we're just going to do the 31.25 minus 2 times 6.340. You can just put 34 if you want. So we get the low end, and then we do the high end. So again, a highlight and an overwrite. So anywhere between 18.57 and 43.93 would be considered unusual. I'm sorry, it would be considered usual. This is the usual interval. So anything that falls outside of these two numbers would be considered unusual. So if you're 18 and a half years old, it would not be unusual for you to be in the NFL. All right. Oh, a little bit older than 18 and a half. But if you're 44 or 46, it would be. Right. So therefore, 44-year-old, year-old.
With the exception of Tom Brady.
With the exception of Tom Brady and I think Drew Brees.
Drew Brees, that was the other guy. Thank you.
No problem. So 44-year-old and 46-year-old players would be considered unusual. All right. And again, context is the driving force behind a lot of things, because, I mean, if like some people are really invested in the NFL, I mean, invested in more ways than one. And then there's plenty of folks that, maybe have a passing interest, and some other people are like, listen,
football is the round ball that's black and white and has like little pentagons and hexagons on it, and you kick it with your foot into a goal. That's football, so the level of interest varies from person to person, but if you know a little bit about the sport, you probably realize that certain players, I don't know what connection was. Oh, it's the keyboard. That's fine. Certain positions can have players that really can play to an older age, and then there's certain positions where you're out of the league after 4 or 5 years because the wear and tear is too much. All right, so it could go either way, but yeah, there's no expectation that you understand that context beyond the simple context of age of NFL players. All right, so age of people. In which case you look at this and say, okay, based off the data, 44 and 46-year-old players would be considered unusual, right? And then that's where you would leave it, right? This isn't like a research project or anything like that. Otherwise, every problem would take us like an entire class session, right? So we're gonna leave that there. Let me just stop this recording, and then we're gonna kick over to the tech assignment because I know we had to do a little bit more with that. Stop this recording.